The chapter what I am dealing with is electrostatics, the study of charges which are at rest on the surface of a body. And this particular chapter deals with electric field intensity, electric potential, and electric capacity. Along with them, the important most applications of linear charge density, surface charge density, and volume charge density as such. So these areas we are going to cover up in this particular chapter, that is electrostatics. Let me just work out few applications taking different model problems over here. Let us take the very first problem of this order. The linear charge density of a thin metallic rod varies with the distance x from one end as lambda is equal to lambda naught x square, where 0 is less than or equal to x, less than or equal to L. That means x lies in between 0 and L. The total charge on the rod is how much? That is a question 1. And of course, options are given this way. First option is lambda naught L cube by 3. Second option is lambda naught L cube by 4. Third option is 2 lambda naught L cube by 3. And fourth option is lambda naught L cube by 2. The correct option for this one is the first option, that is A, lambda naught L cube by 3. How come that be the case? Let us work out first of all the linear charge density of a thin metallic rod. According to him, the question 1, when we talk about, there is a rod taken up of length L over here. Out of this particular rod, let us just consider a small element of length dx. If I just consider this being the origin, the distance to this particular element that is considered, I take that one as x. And obviously, the total length to the other end of this rod, that now becomes L over here. So this is actually the concept what I am considering. Instead of taking the entire rod as a single element, like I consider a small element of thickness dx over there, which is at a distance x from one end of the rod. After calculating the value of linear charge density for this element, I used to integrate that one in between the limits 0 and L as such to get the total charge on that particular rod as such. So this is the methodology what I am adopting to just work out this problem. So let us first of all consider what is linear charge density. Linear charge density, that of course is lambda. We people used to write dq by dx as far as this particular element that is concerned. Charge per unit length, that is what we officially call it as linear charge density. Likewise, suppose if I say surface charge density, charge per unit surface area we people used to take up. So in this particular case, we are dealing with linear charge density here. So I can directly write this equation this way now. This now becomes dq is equal to lambda dx. But officially in the problem, that lambda value is given to us. What is that lambda? Lambda is given lambda naught into x square. That is the value that has been provided to us in this problem. So I just write that in place of lambda. Lambda naught x square dx. But when I just want q from this, in the sense dq is the small charge that is on that length of the element dx. If I want the total charge on the entire rod, then one should integrate that between the limits 0 and the total length of the rod, which is nothing other than L there. So we now can write this implies charge, which is integral of dq, is now integral between the limits 0 and L lambda naught x square dx. And even in the problem also, it's very clearly mentioned that x lies in between 0 and L. 0 means the beginning of the rod. End point is going to be at a distance L from that particular beginning. So you can say the total length is L over here. So between 0 and L, when I integrate this value, I will be getting the total charge on the entire length of this rod as such. That is the basic concept. So if I take up this integration part of it, lambda naught integral 0 to L x square dx. In fact, we all know that integral x square dx is x cube by 3. So lambda naught x cube by 3 in between the limits 0 and L. Now just substitute the upper limit over there. You will be getting the total charge on that entire length of the rod, that is q, now is going to be lambda naught L cube divided by 3. This is going to be the total charge that is there on the rod as such. I just remind you once again, on the entire rod of length L, since he has given you in the problem, this x is lying in between 0 and L. I am considering this itself is the origin here, that is at 0, and the other end of this rod is at a length L. So to calculate the total charge on the entire length of the rod, we imagine or we consider a small element of length dx over there. That is what I have done. This is of length dx, which is at a distance x from the origin. That is the beginning point of this particular rod. So if I take this distance as x, according to the formula, linear charge density lambda now becomes dq over dx, and dq now becomes lambda dx, but lambda is given lambda naught x square. Substituting that value and integrating this value between the limits 0 and L, we be getting lambda naught L cube by 3. This particular option, if you look at of all the 4 options mentioned over there, this is in coincidence with the very first option that has been given in the problem. So the key or the answer for this particular question is going to be A over there. Look at that A, the very first option, lambda naught L cube by 3 as such. That is the correct answer for the charge on the entire length of this particular uniform rod of course uniform cross sectional area there. So this is the very first problem what we have in this order. One of the best models for you to remember, particularly questions on linear charge density. Several times they have mentioned and they have asked in the final examination of JEE.